Okay, it's time to room explanation about to make a proper explanation about transient power angle stability. Okay, uh, mm, I think it's clear already that the transient power angle stability is related with synchronism of the synchronous generator. Okay, and one of the reason is that we have severe disturbance. And like short circuits, loss of generation, very large load disconnections, and faults, of course, short circuits. Okay. Transient stability is determined whether the system is still in synchronism or not after a large disturbance. That large disturbance could be, for instance, the sudden application of a load. That is not quite frequent for big power systems. But loss of generation units, that could be a problem. Okay. However, modern power systems, when we have a very good controllers and very fast acting controllers, and losing synchronism based on losing a generator is not quite typical. It's mainly a problem of frequency. Okay. However, what does mean loss of generation? We are not talking about a very small generator. We are thinking about the biggest generator that you have. For instance, in the UK, we are talking about between 1.8 to 1.4 to 1.8 gigawatts. Okay, that is the loss in feet that you will say that is critical for the GB system. Okay, but today, with the use of very big interconnectors, there is a possibility that if we lose 1 gigawatts or 2 gigawatts interconnector, that is big for many systems. Okay, losing a big interconnector, HVDC interconnector, that is a big disturbance that have effect on the transient stability. Okay, and of course short circuits. Okay, what we need to understand is that when we have those severe disturbance, when we have this severe disturbance, large disturbance, the power system will oscillate. Okay, and what we need to do is take care about how the rotor angle are oscillating. Okay, if the rotor angles they oscillate and then they reach a steady state point, we will say, okay, the system is stable. But if the oscillations start to increase and they take off, okay, the system is unstable, the machines are losing stability. Okay. Um, Bad news. We need to use the swing equation, and we need to use the full expression. I mean, the differential version. The differential equation must be used in order to take in account the performance of the synchronous generators during a large disturbance. Okay, and of course we need to use the nonlinear part of the swing equation. Okay, now the question is, how do I study the transient power angle stability? Okay, basically there are two different approaches. One approach is numerical integration. What does mean numerical integrations? Well, you take all the differential equations defining the electromechanical behavior, for instance, swing equations. You take all those differential equations, then you apply mathematics, and you use numerical analysis to solve the equations. When you solve the equations, you get a time series for the angles, and then you plot the swing equations and you see if the angles are oscillating and reaching a steady state, or if the angles are oscillating and taking off. Okay, that is what probably 99% of the power system analysis software are doing. I mean, power system analysis software, or the majority of them, they use this approach. I mean, creating the differential equations, then apply numerical integration, and then you can plot the angles, and from them you can conclude about the stability, the power system stability. Okay. However, there are another way. Another way is assessing the stability without solving the differential equation. That is the second approach. The second approach is not solving the differential equation, is taking into account mm, taking into account the dynamics, but without solving the differential equation, taking in account another features, you can see, or you can estimate the stability of the system. Okay. There are many methods. There are many methods used for power angle stability, direct methods. Some of them are based on energy balance. When there is a disturbance, the machine try to accelerate, okay? And I say to you that is that the machine is getting energy. But if that energy can be released to the system and the system is able to absorb that energy, and we reach a balance, the system will be stable. Okay. Basically, those direct methods, when they are trying to do, is looking into energy balance, or some approximation similar to energy balance. Okay. One of the most popular methods is called the equal area criterion. Okay. Equal area criterion is basically taking in account the energy balance and estimating if the system is stable or not. Okay. If you are familiar with control analysis, you can see that they are more complex methods to assess stability. Power systems can we can use any control system analysis technique for stability into power system. Okay. If you are familiar with Lyapunov is one of the methods that can be used with energy functions uh, to assess the power system stability. Okay. It's no matter of these classes discussing Lyapunov method of energy method. Okay. If you want to know more, I highly suggest that you subscribe to, or you take my classes about advanced power system or power system dynamics. Okay. Over there, energy functions and Lyapunov, they are considered. Okay. Well, but we can see that there is a method. The method that we will be using in few slides is the equal area criteria. Okay. And what you need to understand is, for transient stability is quite interesting, because when we have a disturbance, a large disturbance, um, we have a sequence of events happening and sequence of stages happening inside the power system. For instance, if we think about the most, let's say, typical large disturbance is the short circuit. And if we think about the short circuit, we can think about three different stages. Pre-fault condition, and that is the conditions that is before anything happening to the power system, and there is equilibrium point over there. Okay, this power system is working at equilibrium point, steady state, delivering power, everything is fine, derivative equals zero, constant speed, there is no acceleration, angle constant, and so on. But then we insert the short circuit. The first thing is that the short circuit imposes a terminal condition. Voltages at the fault location will be zero. We need to take that in account into the power angle equations. Okay. During that period, the power imbalance between mechanical and electrical, they create changes in the power acceleration. That means that the machine, the angles and the rotor speed, they will start to move apart from the equilibrium point. Okay, and that is where some oscillations can happen. And then we have the third stage, that is the post-fault or after fault. The post-fault or after fault is assuming that the fault is clear. I mean, some circuit breakers open and isolated the fault, and the fault is interrupted or clear. Well, if the system is properly designed, the system hopefully will return to a new operating state, and the system will be stable. Okay, that is the best case scenario. What is the worst case scenario? We have pre-fault conditions, the system is faulted, and then the angles start to take off together with the rotor speed, and even after the fault or post-fault, the system has no possibility to recover, and then we will have a blackout. That is the worst case scenario. Okay. Well, what I will do now is to introduce the concept of equal area criterion. Okay. What I will do is introduce the concept of equal area criterion, and let's start with something very simple. Okay. Uh, Imagine that we have any power system. We have any power system. But that power system can be represented like this small system over here, one generator connected to a infinity bus bar, okay? And now I will do something that for academic purposes is quite interesting and useful, but from real life is not so, okay? I know my colleagues from the control rooms in many countries, they will be laughing at the moment because we don't do that, okay? But imagine that we have this generator delivering electrical power to the infinity bus bar, and suddenly we have a power increase. I mean, imagine that somebody intentionally move the mechanical power from 0 to 1, okay? I know that few of my colleagues would say this is crazy. I mean, if you look over there in red color, I am presenting a step change on the mechanical power. That is impossible. I mean, there is no way that we can create a step like that using a turbine, a gas turbine, or a steam turbine, or a hydro turbine. Okay, that is not possible. However, for my explanation, it will be extremely helpful. Okay. For my explanation, I would like to simplify things. There is a step change, initial mechanical power 0, then we have this big change, and the mechanical power goes to mechanical power 1. Okay, what I am showing here is the numerical result from a simulation. Okay, I include over there the numbers just that you can see some feelings about numbers. Okay, but in this case, we are considering here an inertia of 8.45. There is only 10% increase. Look over here, it's only 10% increase, okay? The machine was working at 13 degrees, but when we put a t equal 1 second, the disturbance, and that is the power increase, you can see how the system start to oscillate. The good news is those oscillations, they extinguish in few seconds, okay? Extinguish in few seconds. First, few seconds, a bit more larger than the inertia constant, okay? And and the machine reach a new equilibrium point. I mean, Originally, the synchronous generator was working at steady state conditions. The system was stable, everything was fine, lovely. There is an initial state defined by this delta zero. Then we have the change on mechanical power, and then the machine tried to reach a new state. In fact, reach a new state at 14 degrees. But there is a maximum oscillation. And the maximum oscillation here, you can see the maximum angle is 15 degrees, okay? What I need that you understand is this plot is what we call the swing, the swing curve. The swing curve describes how the angle mm, oscillate during the disturbance, okay? How the angle perform or responds to the disturbance. In this case, we are happy because this situation is completely stable. It's completely stable because the system is oscillating, of course, but there is a damped behavior. The amplitude of those oscillations, they are decreasing. You can see here is decreasing, and the amplitude is decreasing, and the system reach a new steady state point, okay? And that is important. The system is stable, okay? But now, of course, that time domain response, you can obtain that time domain response if you solve the swing equation. If you solve the swing equation, you will get something like that. We will discuss more about that at the very end of this session, but at the moment, I just want to use this plot to teach you the importance of understanding the physical phenomenon behind the transient angle stability, okay? Well, if we neglect the damping, okay, there is no damping in this system, we can use the classical swing equation. We can use the classical swing equation here for analysis, okay? And you can see here, this is the swing equation. What I will do now is few mathematical manipulations in order to demonstrate you why we can reach what is the condition to demonstrate what is the condition that allow me that if this machine has some disturbance, the machine can reach a new steady state point, okay? That is what I'm trying to do. The first step that I will do is I will multiply by the rate of change of the angle delta in both sides, okay? That is what I will do, okay? Okay, if we multiply by the rate of change of delta in both sides, we obtain this interesting product over here, okay? I don't know if you realize, but we are multiplying here the first derivative of delta and by the second derivative of delta, okay? What we will do right now, what we will do is, okay, let's use some properties coming from calculus. That is mathematics 101, okay? And you must remember that the derivative of a function that is squared is equal to times the function multiplied by the FTT. Okay, this is a property. This is a property. The derivative of a function that is square is equal to twice function or two times function and the FTT. But what's happening if we say that the FTT is equal to this delta function? Well, you must realize that that is true. Well, here we have the second derivative, we have the first derivative, and we have here the number 2. Okay? Well, if we follow this property, it's very simple. You can do the calculations at home. We obtain this important property, okay? This important property that say that the product of delta dt dt and the second derivative, and that is here, they can be substituted, they can be, we can use this as an approximation, where is no approximation, is the real value of this product, okay? If we do so, let's do it in the next slides. If we substitute the property here, well, we have a very interesting situation, because first we will have some cancellations over there. Okay, we will have some cancellation. Okay, after using this property here, what we need to do now is multiplying by dt on both sides of the equation. And when we multiply by the IDT in both sides of the expression, that cancel the time dependence on those equations over there, and that's make very simple, because this side will be dependent on this value, and the other side is no longer a differential terms. I mean, what we will do now is integrating in both sides. If we integrate in both sides, one side must be integrated in terms of the delta, d delta, and the other side will be integrated, and this is the differential. When we integrate, the differential disappear, and then we have here this beautiful number that this is the acceleration, this is the rotor acceleration, okay? And on the right-hand side, we have a very important term, because this important term is what is we call the areas, okay? Because at the end you can think about the integral like area, and this is the area that is coming from the difference between mechanical and electrical power, okay? But coming with mathematical development, this square can be, if we apply square root in both sides, we delete this, and that is what we are doing on the right hand side. And then what we need to do is very simple. Um, the quantity that is under the square root over there, this quantity over here is a definite integral, okay? What I am telling you is that this quantity over here, that represent an area, a finite area, and we need to use integration limit for the integration variable delta, and that angle is between 0 and 1, or two angles. That is what we need to understand here. Don't ask what is delta 1 and delta 2. They are two angles, and those angles are coming from the p delta curve that we will see in a few minutes, okay? But coming back to my explanation, what is important is that we say that this term over here represents the acceleration of the rotor, okay? If we are in a steady state, we want that the acceleration must be equal to 0, and also the speed should be equal to 0. I mean, we don't want changes on the rotor angle in a steady state. As a consequence, what will happen is that this quantity over here is the number that must be 0, okay? And this equation over here is the great one, is the important one. Let me move to the next slide, and I will tell you why this equation is important. because this equation over here is what we call as the equal area criteria, okay? Why? If you remember from mathematics, when we are calculating the integral part, we are calculating areas. And to be honest, the difference between the mechanical and electrical power, they define areas in the power angle curve. And those areas, what they are trying to get is a balance. If the sum of those areas is equal to zero, what we can say is, okay, in this case, we are in a steady, we are a possible in a possible steady state operation, and the system is stable. Okay.